Good evening everybody. So, we are still with the electrochemical methods of analysis, and where we are talking about the corresponding redox potentials and how we can measure all these potentials that we have seen. And interestingly, we were able to correlate this thing, that means the measurement of these redox potentials in terms of the combining of two half cells, and the cell potential has also been utilized to monitor the change in hydrogen ion concentration in terms of its pH, and we have utilized that particular measurement of pH in terms of potentiometric titrations for any kind of neutralization reactions. And there also we know the most important shape of the plot, and we see these are the corresponding plots, and we will get somewhere the end point. That means the volume of titrant we add and the potential, electrode potential we measure. So, the same thing whether we will be able to use for other types of reactions, as I told earlier that we can use this for precipitation reaction. Also we can use the same thing for complex formation reactions, and also we can use this for oxidation reduction reactions. So, this determination of redox potentials by potentiometric way or potentiometric method can useful for redox titration curves. So, we will see that what sort of this plot we will get when the two components are responsible like that of our neutralization reaction is for the oxidation of one particular species, say ferrous ions. If we want to determine the corresponding concentration of ferrous ion by a solution of oxidizing agent, which is the ferric ion, as we all know that the ferrous ion present in more salt can also be analyzed in terms of other oxidizing agents such as potassium permanganate, the oxoanionic species, or the potassium dichromate. So, similarly, if we have a standard solution of the ferric ion which can be used for the oxidation of ferrous ion, what sort of potential we can use, because this is the corresponding oxidizing agent. So, it will have a higher redox potential value compared to the corresponding other couples. So, ferric ion will be reduced to ferrous ion, cerium 3 plus. So, these two have some one potential of oxidation, and we also know the very well known and very standard potential for the ferrous-ferric system. So, this we can utilize for this analysis, and also we will take the example of another little bit complex reaction, which is the corresponding reaction with uranium 4 plus, and that is also we are utilizing with that ferric ion solution. That means the standard ferric ion solution, which is your oxidizing agent, can be your ferric ammonium nitrate, can be your ferric ammonium sulfate, even ferric hydroxide, that means CeOH whole 4 can also be useful and also be fine for this sort of analysis. So, this in presence of water basically, because this gives a very useful reaction, because uranium we all know that when you oxidize it, it can go to uranium 5 plus or uranium 6 plus. So, what sort of species we can have once it is oxidized by ferric ion? So, simple ferric ion starting from your organic chemistry or any other chemistry where we can use is a very useful oxidizing agent, and we call some species as CAN, which is the abbreviated form of ferric ammonium nitrate. So, ferric ammonium nitrate can give rise to so many useful reactions. One such is that of your oxidation of your uranium 4 plus, and uranium 4 plus, because we have taken water, so that also gives you some indication that whatever species will be forming over there is the oxo bearing species, that means the oxide bearing species. So, when it goes for higher oxidation state, it has the typical affinity for forming the corresponding uranyl ion. So, UO2 2 plus is forming. This is coming from your water plus for the reaction stoichiometry, because there you have uranium 4 plus is going to uranium 6 plus. So, it is a 2 electron transfer reaction. So, you have 2 C3 plus and the protons which are coming out from the water molecule. So, you require 2 of these water molecules. So, the transfer of this O2 minus from the water molecule can go to your uranium center, but this is a typical redox reaction, and we want to follow this by means of your redox titration. And what sort of redox titration curve we can have? One example we have seen earlier, that in the case of these, that you have the corresponding potential for these two and the potential for these two. So, the E0 values we should know. So, these A0 values are also useful to identify the corresponding titration curve. So, we see the corresponding curve and the value you can have, and say it is 5, 10, 15, 20 and 25. So, okay, 5, 15, 20, 25, which is nothing but the volume of 0.1 molar steric ion solution in milliliter. So, that gives that particular axis, and you have the electrode potential in volt starting from 0.3, then 5, then 7, then 9, then 1.1, 1.3 and 1.5. Is 1.1. So, if we get that, and if we have some idea, because this particular potential what you have, this ferrospheric system we all know, then a standard condition in some 1 molar sulfuric acid condition, it is around 0.77 plus 0.77 volt. So, steric having more higher or bigger higher potential of this can oxidize it. So, the potential for these, that means the ferrospheric system can change, and this can go from here basically. So, it start from here and it goes so this we get for the corresponding values for your Fe2 plus this reaction. But for the other one, how it looks like? So, you get at some point midpoint of this is your end point. That means, whatever amount of ferrous ion was there present in the unknown solution, we can determine by means of the corresponding oxidation by steric ion. So, it would be your Fe2 plus equivalent point, what we can determine. So, this particular thing and also the corresponding uranium one, and this particular potential is less. So, it will above 0.3 volt, and it also goes like this, and you have the corresponding values like this, and it goes like this. So, here basically also you get a potential value for this. Obviously, you have the corresponding concentration in the same range, such that in the same volume range you get the end point. So, it will be your uranium 4 plus equivalent point. So, these things are there that if you have any titration like bearing uranium 4 plus or iron 2 plus, we can determine, and the corresponding redox titration curves will very much similar to that of your neutralization curve, and we will be able to get this particular reaction for your titration, and we get this corresponding endpoint, because these endpoints will be very much useful, and where you have the change in because you see that sudden change. So, you change from 0.5 basically here from 0.5 to 1.4. So, sudden shoot up of the E value when we reach the corresponding endpoint. So, it is in the midway you have the corresponding equivalence point, but this whole range is for changing the corresponding potential of the cell from say 0.4 to 1.4 volt. So, how can we detect those things? Because here we have seen that in potentiometric titrations we can determine this particular one in terms of the corresponding acid base indicators. We have used acid base indicators to detect the corresponding endpoint, which is your endpoint for your neutralization reaction. So, how we detect this endpoint or this endpoint? So, these we can also detect from that of our indicators. So, in this particular case we have the corresponding indicators known as your redox indicators. So, redox indicators will be utilized in a similar way. So, your cell, your electrode and your corresponding reactions can give rise to this particular type of reaction, where we can have that redox indicators. So, these are of two types, and these redox indicators are utilized for to detection of the endpoint. So, to obtain the endpoints like that of your acid base indicators. So, one of this category is of general type, general redox indicator. So, which can change its color on being oxidized or reduced. How it is? This you have a indicator material or substance that change color when it change color, because we know like that of your methyl red or methyl orange, it changes its color due to the proton loss or proton gain. Similarly, here also whether the species is oxidized that means oxidized form or the reduced form, and if these two forms have different color, then you can have the corresponding indicator, and we get a broad range, basically a band. So, when you have this corresponding change, we get a corresponding band. So, at this particular point you have the corresponding reduced color, and at this particular you have the corresponding oxidized form, and we all know that we get the corresponding window for its color change. But for the corresponding one which can be termed as the specific redox indicator, so that specific redox indicator depend on the changes in the electrode potential. So, specifically it can detect the changes in the electrode potential. Here also we are locating, but is a broad type or a band of the corresponding change of color. So, here the specific one changes the or detect the corresponding changes in the electrode potential. So, those we can think and we can use those things. So, in some of these reactions what we can see that we can also use auxiliary oxidizing or reducing agents, because this particular thing, when you have the corresponding analyte which is in the single oxidation state. So, if you have iron, say, when you dissolve it, that means iron in some ore or in some alloy or some metal. So, what happens then? When iron is dissolved, we get a mixture of Fe2 plus Fe3 plus. So, how to use and what is that corresponding auxiliary part? So, auxiliary part, so if you have this, so auxiliary reducing agent we call ARA. So, if we use that auxiliary reducing agent and the analyte solution, what you have? Because just now what we have seen, that iron means you require the whole solution as Fe2 plus, then only you can oxidize it by potassium permanganate, potassium dichromate or steric ion solution. So, this analyte solution should have a single oxidation state. So, we require a single oxidation state, otherwise depending upon the percentages of the individual oxidation states, that means what percentage of ferrous ion is present or the corresponding amount of ferric ion is present, we cannot detect, because this particular reaction can only oxidize, because the steric ion can oxidize only the corresponding presence of the ferrous ion. So, what we do? We use some auxiliary reducing agent which can be able to convert the whole thing, the mixture of the ferrous and ferric ion, to only to Fe2 plus. As we all know from the laboratory methods or the titrimetric method, we use in acidic conditions stannous chloride reduction for this ferric ion reduction. So, stannous chloride reduction can have, you have the corresponding choice for this particular reaction, and that particular reaction can also be utilized for your reduction, that means auxiliary reducing agent can be useful. So, how the different other types of auxiliary reducing agent, we are talking first the auxiliary reducing agent, then we will come to the corresponding oxidizing agent also. So, if you have the corresponding metal ions, that means auxiliary reducing agent where we can use, you can have several metals, and those metals if we can have, say as per example, we can have zinc, we can have aluminum, we can have cadmium, we can have lead, nickel, copper and silver, and say all of them are present in presence of the chloride ion. Suppose we have used hydrochloric acid for the acid dissolution. So, if we use this, that means the corresponding reduction reaction, then you can have the two reductors we can use. These reductors are useful, that means in situ or from some solid support we reduced all of them, or these reductors can be Walden reductors, because it has historical importance in terms of the corresponding introduction by those scientists, or the Jones indicate reductor. So, the Jones reductor is there, and this particular one we can have the corresponding electrons, that means we require these electrons because we are talking about auxiliary reducing agent. So, this auxiliary reducing agent supplying the number of electrons to the species such that it can be reduced to one particular oxidation state like that of your ferric ion. So, Walden reductor is based on silver solid and Cl minus, the reaction which is following, forming AgCl solid plus electron. Similarly, the Jones one can be utilized because the Jones reductor is nothing but the corresponding one as zinc amalgam we call, zinc Hg is the zinc amalgam which is solid in nature. So, this can be useful because this can also have the tendency to reduce H plus to H2, but we have to minimize this particular step of reduction of proton to hydrogen formation. So, hydrogen production should be less, and we use this because the zinc what is present over there in presence of mercury and you have electrons. So, the zinc amalgam which is formed, this amalgam form, and this will give you this electron, or this electron can be utilized for functioning as a auxiliary reducing agent. Similarly, as a counterpart we can have auxiliary oxidizing agents. So, these are auxiliary oxidizing agent, and this can also be very much useful if we take, we all know that one such is NaBiO3. NaBiO3 is sodium bismuthate, and this sodium bismuthate is useful for the oxidation of some metal ion from lower to a higher oxidation state, and this basically undergoes reduction. So, sodium bismuthate undergoes reduction reaction with a 4 proton transfer giving you BiO plus. So, is a oxo species of bismuth, bismuth 3 plus trivalent bismuth, then Na plus is also formed and water. So, what for we basically use? We use this for the conversion of your Mn2 plus. So, Mn2 plus can be oxidized by sodium bismuthate to MnO4 minus. So, the determination of manganese 2 plus can also be achieved by its conversion to permanganate anion, and that permanganate ion can be titrated with a excess addition of more salt or the ferrous ion, and then again we can titrate back to this solution with that of our standard potassium permanganate solution. So, we take this as the solid which is a powder one, and we boil it out in presence of this manganese 2 plus. When all of the manganese is been converted, so you have the excess NaBiO3. So, excess we can filter out to get a clear solution of MnO4 minus. Similarly, the other one, the other auxiliary oxidizing agent which is also well known is your persulfate. So, the persulfate anion is S2O8 2 minus. So, this basically gives us in presence of some catalytic amount of silver ion which can accept electron, 2 electrons forming twice SO4 2 minus, and this basically is going for the corresponding oxidation of the other species. So, you can get to know that you can oxidize with persulfate, that of your bismuthate also, sodium bismuthate. So, here also again the solid one which we can have, or in the solution earlier what we have seen that your sodium bismuthate was filtered out, but in this particular case the excess of the material can be decomposed. So, this excess of this will be decomposed, that means S2O8 2 minus can be decomposed. So, twice of S2O8 2 minus in presence of water can be decomposed back to sulfate and oxygen here. So, twice SO4 2 minus plus O2 which is as gas is liberated plus 4H plus. So, these are basically the corresponding manipulation of using all these things. That means, wherever we are going for handling some solution and that solution is utilized for the corresponding oxidation or the reduction reactions. So, sodium bismuthate as well as persulfate can be useful for your oxidation. Similarly, we have seen that some reductor can be utilized for reducing the species. So, if we want to know that there are certain reducing agents and the titrant, the choice for your titrant solution is that if you have this particular titrant solution, so iron 2 solutions are very much useful. It can be standardized with respect to the standard potassium permanganate solution. So, this particular one, that means the ferrous solution, we all know from other sources that you can have a more salt solution, which is ammonium sulphate, ferrous sulphate double salt. So, this can be very much useful if you have a standard ferrous sulphate solution or more salt solution to determine some of the oxidizing agents also. That means, if you have some alloy, that means it has chromium or manganese. So, this can be converted to dichromate, manganese can be converted to corresponding permanganate, and addition of excess more salt solution we can back titrate the remaining excess of the corresponding more salt for the determination. So, such that these are formed, these are corresponding oxidizing agents. So, we can determine organic peroxides in this fashion also. We can determine chromium 6 like that of your dichromate or chromate, then we can determine cerium 4, we can determine molybdenum 6, then nitrate, chlorate, etc. So, this is one such solution. Then sodium thiosulfate solution, Na2H2O3 solution, which is not a standard solution, you have to standardize it. So, that sodium thiosulfate solution can be useful for the other oxidizing agents. So, this sodium thiosulfate is the reducing agent. So, we can have the corresponding is a nitrate is for the determination of iodate or periodate, IO3 minus and IO4 minus, or nitrite. These can be very usefully determined by means of the corresponding titration with standard solutions. Then, as I told you that this particular one, that means the corresponding use of the oxidizing agent, that means the KMnO4, K2Cr2O7, because they have the corresponding known potential values of 1.51 and 1.33 volt. Then ferric ion also 1.44 volt. But if we try to go something for that reaction, that means the corresponding redox reaction, that means the metal complex like that of our iron with the corresponding one as your orthophenanthroline, which is this particular bidentate ligand, which can bind to your Fe2, and 3 such is there giving you the corresponding octahedral complex, and this can have a good color change for these 2 different oxidation states. So, for the determination of cerium in the solution, so which is giving the corresponding indicator as your ferroin, the corresponding ferrous orthophenanthroline solution. So, this ferroin is the indicator, so is a good redox indicator, and it can change its color from pale blue, which is the oxidized form, to the red one, which is the reduced form with a potential value for 1.114. So, we see that within this particular potential range, we can use this as the indicator for some redox titration, and if we can have some substitutions on it, So, it is 1, 2, 3, 4, 5. So, this is the 5 position of these. So, substitutions on 5 positions by nitro group or methyl groups can change the corresponding potential values from 1.11 to plus 1.25 volt for your nitro one and 1.02 volt, which is going down due to the presence of methyl function. So, within this whole range of 1.02 volt to 1.25 volt, you can use this particular one for the corresponding redox titrations, where we can use this as the good redox indicator, because it can change its color from pale blue to red. And all these things we can utilize nicely for your corresponding reactions, where we come to know that these potential values are very much useful for the different electrode potentials. And the corresponding values are changing. So, how the corresponding E0 values for the reaction cell, which is getting changed for all these reactions, whether we use KMnO4 or K2Cr2O7. So, this cell potential is always very much important, and some of these reactions, as we have just now seen, that for your ferroin indicator. But what we use for these two, that means when we use these, that means whenever we use these as the oxidizing agent, so your substrate can be oxidized, and this will you can use, and at this point you just ask yourself that whether we need any indicator or not. And since it is a traditional knowledge of permanganate titration from your school level or college level, you can immediately say that no, we do not want any indicator, because your potassium permanganate is self indicating. That means you get something that where you get the corresponding endpoint, and this endpoint is known by the extra drop of potassium permanganate, which is violet in color. So, the entire solution can be colored by this. But when you go for your potassium dichromate solution, and this dichromate solution is not so clearly visible like that of your potassium permanganate. So, we use one indicator which is abbreviated as BDS, which is barium diphenyl amine sulfonate, and this can be oxidized. So, this sulfonate diphenyl amine can be oxidized and coupled together at a potential value of plus 85 volt, 0.85 volt, and its oxidized form is red violet in color. So, when the reducing agent is fully oxidized by your potassium dichromate, finally the indicator will be oxidized and the endpoint is marked by the color change from some dilute solution color depending upon the species which are present, but finally the whole solution will be red violet in color. Okay, thank you very much for this part of your course.